So good afternoon, everyone. Welcome to the final lecture of the Taiwan Space Union Focus online course. Today, my topic is integrating multi-source geospatial data and IoT for disaster management. And the main idea is very simple. We're moving from the traditional maps to real-time monitoring and from data collection to decision making. So I'll use Taiwan's experience to show how the GIS, IoT, remote sensing, UAV, AI, and all the digital twins can support the disaster resilience. My name is Tien-Yin. I'm the professor in the GIS Research Center in Fengjiao University. My background is from the soil and water conservation, resource development, GIS remote sensing, and disaster management. I'm also involved in the OGC Asia Forum and APFITA. So over the years, I've been closely work with the governmental agencies on the slope monitoring, disaster warning, sensor integration, UAV application, and digital twin systems. So I think from the global epicenter, the Taiwan is located in a very challenging region. The Western North Pacific produce more tropical cyclones, or we say typhoon, than any other region in the world. So Taiwan is often located along the path of this kind of storms. So we have very serious typhoon during the summer season. And also, beside the typhoon, Taiwan is also located in very, we say, active earthquake zone. It's between the Philippine Sea Plate and the Eurasian Plate. So these two plates crush each other. So especially in the eastern Taiwan and the central region, the earthquake can weaken the slopes, and later heavy rainfall may trigger the landslides or debris flows. So in Taiwan, earthquake risk and rainfall risk are closely connected. And this is the special pattern of the earthquakes in Taiwan from 1900 to 2025. So you can see a very strong concentration of the earthquake epicenters along the eastern area in Taiwan. However, some kind of shallow inland earthquake in western Taiwan also being very destructive, just such as one of the Chi earthquake, very serious one with a Richter scale of 7.3, killed almost 4,000 people just in that earthquake event. So that's a very serious and very exposure and vulnerable for entire Taiwan. So this is something we have to focus on. So the challenge in Taiwan's slopeland management is Taiwan is very limited by our flatland. We have only 1/4 of land is flatland. So the other slopeland or high mountain area creates major challenge for land use, infrastructure, and also disaster prevention. With the climate change, the rainfall events are becoming more extreme and concentrated now. So Taiwan also have very steep terrain and fragile geology. So landslide and debris flow are very frequent, especially during the typhoons and very heavy rainfall events. And if we see the sediment disaster in Taiwan, is really highly related to the rainfall. So most of the typhoon season is during the summer season. So it's a main typhoon and heavy rainfall season. And the threshold between like 200 to 650 millimeters, or sometimes around the 650 millimeters. So the probability of this kind of sediment disaster become very, very high each year. So rainfall monitoring and rainfall-based warning models are very important in Taiwan. As this one, we can see, for example, like this curve, this is one of the very, very heavy rainfall. It just happened just last year. So this rainfall has a cumulative amount to more than 2,000. And one of historical one is almost near 3,000 millimeter of rainfall, putting down from the sky in almost 4 days in the 2009, the typhoon Mora. So normally we say each typhoon will bring about sometimes over 1,000 or just 500. So these are some of the typhoon events. So as you can see, we have very, very high rainfall amount. Just like showing this one, this is one of the gasoline station near the central Taiwan. So in the year of 2000, there's several rainfall, different months. And it all happened with a debris flow and some kind of landslide. So it buried the entire gasoline station. And so even in the year 2000 and also in the 2004 or 2008, even in the 2023. So several typhoon events, several high rainfall events were covered the entire gasoline station. So this is what's happening in Taiwan in some of the places. So this is why we are very concerned about Taiwan's environmental monitoring, because our environment is very fragile and also sensitive. So environment monitoring is very essential. We need different types of the equipment to observe the rainfall, the soil moisture, the water level, the slope movement, the ground vibration, and even the field images. So the goal is not only to collect data, but also to detect abnormal changes before any kind of disaster becomes serious. So when monitoring data is connected to the GIS and warning models, it becomes useful information for early warning and emergency response. So this is why we're very focused on this kind of things. So there's an interoperability between the agencies. For example, disaster management involves many different governmental agencies, and for example, the Forest Agency and Soil Water Conservation Agency and also the Water Resource Agency, they all have their territory in charge of different territory places in Taiwan, even in the slopeland. But during a disaster, decision makers need to see the entire, we say the whole picture, not only one agency's information. So if all this kind of data cannot be shared or integrated, the response becomes very slow. And this is why the interoperability between agencies is so important for effective disaster management. So this is one of the very important things as an interoperability to exchange all this kind of data. So why the standards matter? Because different standards always speak differently. So some use a shapefile, some use database, some use the WMS, WFS, and some even use the sensor loggers or CSV files. So during the normal time, this may only be inconvenient, but during the disaster, it becomes a very serious problem. So we need standards. We need maps, sensor, database, and government system can exchange all this kind of information quickly and correctly. So in real disaster management, we must integrate many different services and data sources. This may include water resources system, KML fire sensor network, monitoring station, web services, and real-time data streams. These systems may have different formats and communication methods. During disaster, users need fast request and response. So therefore, disaster platform must be designed to integrate the different data sources from the beginning. And also, the standards are the common language of disaster resilience. The disaster response may fail when agencies and systems cannot communicate with each other. Taiwan used the Common Alerting Protocol, the CAP, to standardize a lot of alert messages. We use also like ODC, the Sensor Things API, to connect different sensors. With this kind of standards, the data can move from field monitoring to platform, from platform to agencies, and from agencies to the public. So data becomes decisions, and decisions become actions. And the Common Alerting Protocol can help standardize the disaster alerting messages in Taiwan. It collects warning, messages from different governmental authorities and publishes them into a consistent format. A good alert should explain how issued it, what happened, when and where it happened, why it matters, and how people should respond. So the common alerting protocol allows the warning information to be shared between website, apps, social medias, IoT products, and public information services. So this is why the standard is really, really important. And the different type of the slope and disaster monitoring stations in Taiwan include such as debit flow stations, sediment monitoring station, landslide monitoring station, and automatic rainfall stations. Each station has different rule, like rain gauge measure the rainfall, the camera provide a visual confirmation, the geophone detect the vibration, and the other sensor monitor slope or channel conditions. So together, these kind of stations form a monitoring network for slope disaster prevention in Taiwan, and it worked very well in the past 20 to 25 years already. And also, this is a kind of portable monitoring unit designed for very flexible and rapid deployment. It includes a solar panel, a rain gauge, a soil moisture sensor, a geophone, a radio communication, power system, data transmitted, and control module. The advantage is that it can be installed quickly in the high-risk areas where permanent stations are not available. So after the earthquake, typhoon, or field investigation, this kind of portable units can help agencies monitor the new or temporary risk locations. And also, not only this, but also the mobile facility. So the mobile monitoring facility provides another flexible solution for disaster management. So because sometimes we cannot build a permanent monitoring station very quickly, and also it's very costly. But we still need real-time observation near dangerous slope or river channel or bridge or even community. So mobile facility can be moved to the required location before or during any kind of emergency. They bring sensing, communication, and field observation capacity closer to the disaster site and help the agency respond faster. And this is the inside and outside of a new mobile monitoring stations in Taiwan. Include electricity system, generator, telecommunication system, information system, even the NB-IoT and NB-IoT communication, the cameras, and rain gauge. So in this kind of remote mountain area, power communication may not be very stable. So the station must operate independently. So it can collect rainfall and image data and transmit real-time information and support both the field teams and the emergency operations centers. So it worked very well. And also the overall slope-land monitoring system in Taiwan is on the field side. We have the monitoring station, mobile station, portable unit cameras, soil moisture sensors, geophones, wire sensors, and rain gauge. For communication, we may use satellite. We may use internet. We may use a microwave, the 4G, the 5G, even the LoRa or the NB-IoT. So on the decision side, data is sent to the emergency operation centers, dashboard, and mobile apps for analysis and response. So there are lots of this kind of high tech being used. And disaster prevention decision support system connect with the sensing equipment, the communication networking, and emergency operating centers and application. So it can be used for not only for the debit flow, but also for sediment monitoring, ecosystem, landslides, and bridge safety. The system integrated technologies such as wireless sensor networks, sensor things API, satellite communication, fiber, 5G, LoRa, NB-IoT. The goal is not only to display data, but also to support the alerting, the reports, and the decisions. So that's the most important things. And this slide shows how the field monitoring worked during the debit flow events. So there's on the left-hand side, there's a sensor, the vibration, has been detected in the upstream 20 minutes ago. So in the middle stream, we can see on the camera, it record a very serious debris flow event. So the reason for that is because we have lots of this kind of sensor being deployed or being stored in the Wild Creek area, where it has a very high potential risk for this kind of debris flow or some kind of floods or any kind of thing. So there are lots of this kind of sensor provide the real-time information. But the goal is not only for the display the data, but also to support and alert and reports and also the decisions. So as we can see in this one sensor, it might be malfunction. So we need to have the sensor talk to each other. For example, if the camera identifies there are something being happening on the slope land, so it automatically from green light to yellow light, and it double check with the rain gauge amount, with the water level, with the velocity. So make sure it's not just camera malfunction, because it will announce us there is a debris flow event really happen in the field. So this kind of machine-to-machine communication is also very, very important. So this kind of slide to integrate the large-scale landslide is very, very complex. So you need to integrate many monitoring devices and the data type. So this kind of system combines automatic sensors and semi-automatic equipment, the manually observation rainfall data and displacement data, and also the radar imagery. So the dashboard allowed the expert to compare with the rainfall, slope movement, and warning information in one place. So if a rainfall increased and displacement also accelerates, the risk may be rising. This helps the decision makers respond more quickly. So, and also the rainfall-based warning model for debris flow and large-scale landslide, the system compares the forecast rainfall and real rainfall with the warning thresholds. So when predicted rainfall exceeds the threshold, a yellow warning may be issued, and local government may advise the evacuation. When real rainfall exceeds the threshold, a red warning may be issued. A mandatory evacuation may be required following the Disaster Act. So the technical warning must connect to the real action. So this is how being operate in Taiwan for many, many years. And it works very well. So the alert map application integrates disaster alert and historical emergency response incident into a spatial platform. So this is where the GIS come in. The user can switch between the map mode and list mode, the filter different alert types and view events at the different map scales. The timeline function is also useful because disaster change over time. So this platform helps the users answer two very important questions during emergency response. Where is the event? And also, when did it happen? So this is very important for any decision-making things. So issuing a warning is not enough. The warning must reach the right people at the right time. So Taiwan uses different channels, including the websites, the API services, the public warning system, even the Facebook or professional volunteer or the line. So different people receive information in different ways. So one single channel is not enough. A warning becomes useful only when people receive it, understand it, trust it, and know what action to take. So the last mile is one of the most difficult part of the warning dissemination. Cell broadcasting technique in Taiwan can send localized alert directly to mobile phones with very low delay. So professional volunteer can verify field conditions and also report the local information through the apps. And the line chatbots can provide evacuation maps and emergency supply checklists. A warning system should not only tell people that danger exists, they should also help people and take actions immediately. So this is also very, very important in the last miles. And before a disaster happens, the local government, they need to check the drainage system, the pipes, the pumps, and emergency equipment. So in the past, it was difficult to know the real-time status of the preparation and maintenance. With the cloud inspection app, field workers can upload the inspection result immediately, and managers can see the overall situation through the dashboards and schedule resources more effectively. This shows the digital disaster management also support the preparation before the disaster. So before any kind of the big data and the AI can really support the flood forecasting. So in the past, it was difficult to predict where flooding would happen during the heavy rainfall. But by the combination of the radar echo data, the rainfall station, the AI machine learning, the cloud computing, and 1D, 2D, and 3D water models, the system can forecast rainfall and flooding for the next 1 to 3 hours. So this gives agencies more time to operate the water gates and even the pumps. So in Taiwan, this kind of disaster emergency system being worked out very, very well. And during the disaster, the report may come from many different sources, including the public reports, the flooded station, the different kind of APIs, and line bots, and field systems. So in the past, processing this kind of reports require a lot of manpower and time. So a cloud disaster response system can automatically assign cases and show alert statistics and display spatial distributions, and also to support quick reporting. So this can help command centers understand the situation faster and improves the emergency decision making. So this is being really work out very well between different kind of GIS technology with the cloud, with the communication, with the field information. So after or even during a flooding event, we also need to understand why the flooding happened and how serious the damage is. So this kind of system can integrate the rainfall, the flooding depth, the river water level, the sewer water level, the three-dimensional terrain, the land use, the population density, the building data, and agricultural damage information. So by combining all this kind of data, decision maker can analyze the causes and estimate the impacts, and also to improve the future planning. So this supports both the emergency response and post-disaster review. So this kind of GIS systems and also the real-time information can really help. And the AI image recognition for the flood and alerting integration is also very important. For example, the kind of virtual water gauges, the tire heights, can identify what is the flooding depth currently, like 11 or 10 or 12 centimeters on the street. So it helped a lot. So it can integrate the flooding depths, the kind of lots of information through the CCTV images. So this can reduce the need for the manual monitoring and saves manpower. More important, it helps answer 3 key questions. What happened? What did it happen? And when did it happen? So this makes disaster information more timely and actionable. So this kind of the disaster reduction smart cloud system can really help. The traditional two-dimensional, the flood information is sometimes difficult for the user to understand. So this slide shows the idea of the three-dimensional disaster reduction smart cloud system. So in Taiwan, by using this kind of three-dimensional simulation, we can really create a digital clone of a city and show the building flooding, the pipeline locations, the detention pond water levels, and channel changes. This makes the disaster information more intuitive and helps the engineer, the planners, and emergency managers can communicate more clearly. So through this kind of three-dimensional way, we'll be able to see what's happening now and also to estimate or to get to know what's the next step we need to know or we need to do or how we can act. And this is a kind of the AI integration of the weather data. So the AI can integrate, for example, this one, the AI can integrate the meteorological data and spatial information to support disaster risk. For example, the AI will be able to estimate, like there will be the typhoon, the future typhoon prediction just 2 weeks ago. So the AI will be able to predict or to make some kind of estimation or even check this one. What will happen when the rainfall exceeds the 300 millimeter or 400 or 500? So use this kind of hydrological model joined together with the two-dimensional GIS and three-dimensional the terrain model, the building model, then we'll be able to estimate a lot of things. And we can let the AI learn by next time. So the AI becomes smarter and smarter each time because they learn. They estimate, they learn, then they remodel it and have some kind of feedback. So this kind of simulation is really help to the decision-making person and also help a lot of things. So like this kind of AI image recognition system, this slide summarizes the AI image recognition system. It connects mainly the CCTV image sources from water resource agencies, from local government, from the industrial parks, and vehicle-mounted cameras. So the system uses image preprocessing, semantic segmentation, and deep lab version 3+, and day and night models, HSV color simulation, and generative AI support. It can detect the road flooding, the bridge water levels, the water gauges, the people, the equipment. So the main benefits of this kind of platform are reducing the workload and improving response efficiently. So in Taiwan, currently, like we are monitoring tens of thousands of this kind of camera. All the camera belong to different agencies, but they all use the same kind of standards to publish all the information out. So use this kind of information, we'll be able to estimate, we'll be able to get to know what is happening in the field. So what's the real data and what's being estimated things. So using this kind of things, we'll be able to do lots of things. And currently, the UAV has been very, very helpful in many, many ways. So it's been very helpful for disaster management because they can collect information very quickly and safely. So in the dangerous or very hard to access areas, the drones can support emergency surveillance, the slope stability analysis, and thermal images. So they can capture the high resolution images after the landslides, the floods, the fire, or infrastructure damages. For example, the thermal cameras can detect the heat sources, while the visible image can support the mapping and change detections. So the drone provides a very flexible and detailed spatial information for disaster response. So in Taiwan, the drone operation is also one of the very, very important sources and very good facilities. So this slide summarizes the technology information. We say the GIS provides the spatial context by helping us to understand where things are and how they are connected. And the remote sensing provide repeat observations through satellite or UAVs or aerial images or the thermal sensors and field sensors. The AI transform all the images into intelligence through detection, prediction, and decision support. So when we say the digital twin connect analysis with action through the 3D cities, dashboards, data cubes, and real-time platforms. So from data to decision and from monitoring to resilience, the main message of today's lecture is that the disaster management must move from the data to decisions and from monitoring to resilience. So we need to integrated sensings, the artificial intelligence, the Internet of Things, the drones, the UAVs, the GIS, the digital twins, and open standards. We also need the real-time monitoring, the early warning, and decision support. So Taiwan's experience in the debris flow, the slopeland, the flooding, and even for the urban risk shows that the technology can help us to build a safer and smarter communities. So through this kind of action, through this kind of process, we create a digital twin with the sensing by the standard. So this is a very, very important thing. So I think this comes to the end of today's lecture. I think the GIS focus course series by the Taiwan Space Agencies, across the 3 lectures, we connected the spatial data, the AI, the sustainability, the agriculture, the disaster management, and also the decision making. So the first lecture was focused on the GIS and remote sensing for the sustainability. The second one, we discussed the AI in agriculture and weather alerts. So today's final lecture focused on the geospatial data and the IoT for the disaster management. So get together, this kind of topics show the value and the space observation for a sustainable future. So I think this is the end of my 3 course lectures during this July. And thank you very much for your listening and join me together. So before we finish that, I would like to briefly also to advertise the Asia Pacific Federation for Information Technology in Agriculture Conference. We say EPIFITA. And EPIFITA promotes the use of the information technology, the AI, the geospatial technology, and digital tools in agriculture and sustainabilities. So this year in 2026, EPIFITA will be held in Taipei, Taiwan. So last year was in Indonesia, and before last year was in Japan. And in the previous almost 30 years, it been hosted in in many countries like Philippines, India, even lots of countries, Thailand. So we very warmly welcome the researchers, the students, the government partners, industrial professionals to join us and exchange the ideas on a smart agriculture and sustainable development. And hopefully we'll be able to see you this November 4th to 6th in Taipei, and you're all welcome to join this very, very good conference seminar. So let's finish with a very, very short quiz to review the entire idea. Thank you again for joining me today. So I think this is the third lecture of my online courses about about the remote sensing, about the GIS, about the AI, about the digital twin in the different aspects.